has to do with money. So in this particular example, we're going to be looking at investing some initial deposit and looking at a function that estimates how much money I'm earning in interest and how much money will be in the account after so many years. And it's a rate of change, dollars per year, that we'll be looking at. So to get started with this one, let's go ahead and look at an investment with an initial deposit of $100. The balance in the bank account after t years is given by this function right here, f of t equals 100 times 1.08 to the t. Notice here that the base of t, the exponent t, is 1.08. 100 is not raised to the t power. A couple other things to look at here that are interesting. This function is not arbitrary. This $100 is related to 100 in my function here, and this we're going to figure out is related to interest rate. So again, this is not a function that we just kind of came up with out of the blue. It's one that's used quite often when we're looking at banking type problems. The first question I want to know is, what are the units of the rate of change of f of t? Well, in this particular case, the units wouldn't make sense to be miles per hour because we're looking at a different type of an example. Our units would be dollars per year. So that's our rate of change that we're looking at. The next question that might be of interest is to find the average velocity, or sorry, in this case we're not going to use velocity, we're going to use rates of change. So find the average rate of change over two different intervals. So you're going to want to use your calculators for this one. So the average rate of change over our first interval will be between 0 and a half of a year. That's where 0.5 comes in. And the second one that we're going to find is our average rate of change between 0 and 1 year. Now, because this is based on $100, from here it will be very easy to surmise what the interest rate on this particular account is. So our first example, let's go ahead and find the average rate of change. Over the interval 0 to 1/2 year. Well, we already know that our average rate of change will be our terminal minus our initial position and our terminal minus our initial time. So for this particular case, I'm going to have to plug in some numbers here. This is going to be 100 times 1.08 to the 0.5 minus 100 times 1.08 to the 0 over 0.5 minus 0. Okay, if you run and plug and chug through these numbers, you're going to come up with 103.923 minus 100, which was our initial investment at time equals 0, divided by 0.5. And what I come up with here is $7.8461 per year. Okay, so of course we'd round that to $7.85 per year. So that's our average rate of change over half of a year. And you might say, well, if I want to find the average rate of change over the entire year, I should just double that. But this is not a linear function. This was a base to a power, so this is not a linear type function. The next thing we want to do is find our other average rate of change over our other interval, 0 to 1 year. So this would be our function evaluated at 1 minus our function evaluated at 0 over our time of 1 minus 0. So for this particular case, I'd have 100 times 1.08 to the first minus 100 times 1.08 to the 0. And of course 1 minus 0 is easy enough to work with. And what we end up with here then, and of course here, anything to the first power so far that we're looking at will just be itself. So 100 times 1.08 is 108. Over here, anything to the 0 power is 1. 100 times 1, of course, is 100, divided by 1. And here I get $8 per year. Well, if I invest $100 and at the end of that year that I've invested it in, my average rate of change was $8, meaning I have $108 in the account at the end of the year, I got 8% interest. The next thing we want to do for part C here is I would like to estimate And again, we can't do this without calculus here. So I want to estimate the instantaneous rate of change. And again, ROC is shorthand for rate of change at t equals 0.5. So that means at half of year I want to look at that instantaneous rate of change and estimate it. And I'm going to estimate this by computing the average rate of change to the left and right of t equals 0.5. So from here, again, this table basically represents I'm trying to determine the instantaneous rate of change right here at 0.5. Now I can't find the instantaneous rate of change at 0.5 because remember, my denominator of my function, change in s over change of t, would go to 0. So what I'm going to do is I'm going to choose some intervals to work with that are very small intervals, and I'm going to do the same problem I did just above, except with much smaller intervals. So I'm going to be looking at the average rate of change between 0.49 and 0.5 years, between 0.499 and 0.5 years, and 0.499 and 0.5 years. And that's kind of going to give me an idea of what's going on to the left, or less than 5 or half of a year, and then to the right, or slightly above half of a year. So up here in this direction I'll be looking at 0.5 to 0.5001, and there's nothing magic about the numbers we're picking here. You could choose other intervals, but we want very, very small intervals to be working with. So this is kind of what we're looking at. Now, this box will represent the change in our function. So this will be f of t evaluated at 0.5 minus f of t evaluated at 0.49. This box, or this row, will basically represent the change in time. And then this last one is kind of like our answer box. It's going to be the ratio of these two. So this will be the change in f over the change in t. So you're going to want to get out your calculators here and plug and chug through these. Now each of these problems I'm doing is exactly identical to these problems that I did up here. We have just changed the interval. So I'm going to pause for a minute while I work these problems and fill out the table. This would be a good chance for you to break out Maple and start chugging in some numbers. It's also a really good time for an Excel spreadsheet, or getting out your nice old TI and getting to work on it. But fill out this table and you'll start to see some really interesting trends appear. Okay, after you fill out their table, this is the results that you get. But again, you want to make sure you go through and verify these, because you should be able to do these types of problems. I'm going to pull out one of these and just go over it one more time by hand just to clarify. So what we're looking at here is the average rate of change over the interval 0.49 to 0.5. So in this particular case, it's the change in your function. Instead of our position function, we have a financial function here over the change in time. So this would be f of 0.5 minus f of 0, or sorry, not 0 in this case, 0.49 over 0.5 minus 0.49. And of course we can see up here this 0.5 minus 0.49 is right here, so these match. And if we take these values and plug them into my original function, 100 times 1.08 to the 0.5 minus 100 times 1.08 to the 0.49, and again my denominator is 0.01, we can see that we get these numbers from the table. Now in our numerator, it's important to carry out your decimals as far as you can. You don't want to do any rounding if you can be at all avoided, because we want to get pretty accurate estimates here of this average rate of change. So in this particular case, when we divide by this decimal, of course we move the decimal 2 places to the right, and I end up with $7.9949 per year. This is our average rate of change for this particular box, for this particular estimate right here. And I fill out all these boxes the same way by doing the same formula. That's why the comment about the Excel spreadsheet being handy is very true here. Now what I'd like you to do is to look at some trends. From here, it appears that when I approach this particular direction, I can see a pattern. and when I approach this particular direction I see a pattern as well. The interest rates here are approaching about 8%. The interest rates over here are approaching that 8% value as well. So I think that this estimate of 8% for my interest rate is a very good one. And I can see this trend by approaching either value works pretty slick. And I'm not sure what happened to all of my table here, but if you rewind the video, you should be able to get all those values from the table, and I'll try and fix it up for my notes. So again, I estimate the instantaneous rate of change at a half of year is about $8 per year, which relates to 8% interest. And that relates back to my formula, 1.08 is where the 8% interest comes into the T. So basically, average rate of change conveys to approaching or getting close to instantaneous velocity. So average rate of change converges to or approaches instantaneous velocity. Okay, I fixed the table back up, so hopefully you can see it back in its screen. Lesson learned, don't use my highlighter. The highlighter seems to mess everything up, so I'll try and avoid that from now. But what we come up with here then is a good estimate for our instantaneous rate of change using this average rate of change over a very, very small interval. And of course, if we check a lot of intervals, we can see it gets closer and closer here. So what we can end up saying here is that the average rate of change converges, and one of the ways we use to represent converges goes toward approaches instantaneous velocity. And so that's cool. Very exciting. The next thing we want to look at is instantaneous rate of change, which implies velocity, but instead of in a money example, let's go ahead and look at this graphically. So when we look at this graphically, first of all, we need to think about our position function and our time function. So for this particular look, we're going to be looking at our position function on the vertical axis, and we're going to be looking at two positions, our position at our initial time t0 and our position at our terminal time t1. Okay, so that's kind of our first look here. Now on our horizontal axis I have time. So I have my initial time and my ending or my terminal time. So what we can look at here is just some graph. We can see that these points intersect. t0 plugged in gives me s of t0 up here. I'm going to be looking at an increasing function that has negative concavity. So this is the function I'm looking at. Now this is not based on a function that I'm being given. This is just a quick curve sketch. So this is the graph of s of t at different times of t. Specifically, we're looking at between t0 and t1. So these are our positions. Now what I can draw between these 2 points is a secant line. Let's see if I can hit it. Yep, got it. So this is a secant line. Now as we talked about a tangent line before, skimming a graph, a secant line intersects or cuts the graph at 2 points in this particular case. So for this secant line, I might be interested in finding the slope. Well, the slope is pretty easy. It's a change in y or the change in x. That's our typical representation of the slope. But in this case, we don't have an x and a y axis. Our vertical axis is the change in position over the change in time. Well, this should look familiar. This is just average velocity. So there's a relationship between velocity and slopes of tangent lines as well. So this is an example of interpreting velocity as slope. And we're going to use this idea quite a bit.